The 7 points, lines, planes, postulates. Remember that a postulate is an agreed upon rule and that no proof is needed. What we're going to begin with is looking at 7 postulates that apply to geometry. Okay, these are going to be using the points, the lines, and the planes, those undefined terms that we have previously discussed. Okay, all the things that we see here are all going to be true things that we do not have to prove. We accept that they are true because they logically make sense. All right, number 1, through any 2 points, there exists exactly 1 line. All right, so what I'm going to do is sketch pictures of these things just to kind of highlight what's happening. Because each of these statements sort of has a beginning part and then it has a concluding part that goes with it. Okay, and in order to really highlight that as well, what I'm going to do is use 2 different colors when I draw this. Okay, so I'm going to use a blue color to do the beginning part, and then I'm going to use a red color to show the sort of conclusion part to each of these. All right, so number 1 says, through any 2 points, there exists exactly 1 line. Okay, so what that means is that we start with 2 points, and I just have them randomly placed on this little card. We've got 2 points. Given those 2 points, there exists exactly 1 line. What that means is that if I were to connect these together, there is only 1 possible line that I can draw. And that line would be this guy here. Okay, what it's telling us is that not only can we connect those 2, but you cannot connect them in any other way with a line, which in geometry we're assuming a line is a straight line. Okay, and again, this is a postulate. There is no proof that goes with it. This is something that logically we should be able to see and then just accept as truth. Postulate 2, a line contains at least 2 points. All right, now if you compare number 1 and number 2, they pretty much seem like the same thing, right? Because we're talking about a line and we're talking about a couple of points here. All right, but it's a matter of perspective with how these are written. All right, so in number 2, we don't actually start with the points, we start with a line. All right, we have a line that exists, and what it says is that line will contain at least 2 points. Okay, now if a line goes on infinitely, it really does include an infinite number of points because you could literally put a dot wherever you want on it. Okay, but at the bare minimum, it's going to have at least 2 points. You cannot have a line that only has 1 point. That wouldn't make sense. So this is a little bit of an odd one. We stated as saying at least 2 points, but the truth is that a line, when it goes on forever, it actually has an infinite number of points that would be on that. All right, so again, the differences between those 2. Postulate 1, we start with the points. Okay, I did that in the blue color. We start with the points, and then we can draw a line, a single line, exactly 1 line through them. In postulate 2, we start with a line, and then notice that we can have multiple points sitting on top of it. Okay, postulate 3, if 2 lines intersect, then their intersection is exactly 1 point. Exactly 1 point. All right, so starting, I'm going to use my blue color here. We're going to start, we have 1 line. All right, now if another line exists and it didn't actually make contact with it, then that would be a line that would run parallel to it. Just going to make sure I don't draw it parallel. All right, they make contact. And I could do that in a number of different ways, but I'm just making sure that they run into each other. When that happens, you can only get 1 intersection point. You get exactly 1 point. It is impossible for 2 lines if they are straight lines, and that's how we see them in our geometry here. If we have 2 straight lines to intersect, they're only going to intersect at 1 point. All right, postulate 4, through any 3 non-collinear points, that's a key thing, non-collinear points, there exists exactly 1 plane. All right, so we are going to start with 3 points. All right, and given any 3 points, they can all be positioned into a plane together, or better said here, a plane. Should probably extend that out a little bit more. A plane, a single plane can be built around these 3 points. Okay. This is a little bit of a tough one to really describe. You have to imagine it in three-dimensional space to really get it. But you have these three dots that just sort of exist. They're out there. Any 2 points, you could connect a line through them. Okay, and I want you to imagine there's a line right there. And through that line, I could have an infinite number of planes that slice through it. I can have the one that appears to go horizontal here. I could also have a plane that would go vertical into those, and then I can have planes that go diagonal into those 2 points. Through any 2 points, you can have an infinite number of planes that are in there. But as soon as you put a third one in there, it almost like gives you a tilt to that plane. And in this case, the way that I'm attempting to draw it here, that plane ends up being the horizontal. Okay, but if maybe I made that point float above these two, I would have to draw a plane that would be in a vertical positioning. Okay, so that does come back to this word here, non-collinear. If the 3 points that you have are in a straight line, then you can literally have an infinite number of planes slicing through that just at different directions. All right, postulate 5. A plane contains at least 3 non-collinear points. That is a lot like number 4 in the same way that number 2 and number 1 were sort of like each other. What we start with in this case is a plane. Okay, so we'll draw that up first. Okay, so we have a plane that already exists, and if you went to that plane, so just think of it as like a tabletop. For this, you can easily identify 3 points that would be on the plane. Again, if a plane is infinite in its size, it's actually going to have an infinite number of points on it, but at bare minimum, it's going to have 3 of them that are non-collinear. All right, postulate 6, if 2 planes intersect. This is a tricky one here. If 2 planes intersect, then their intersection is exactly one line. The really hard part to grasp sometimes with this is that when we draw our planes, we draw them where they look like they have boundaries, that there's a fixed size to them. But the truth is that they actually extend on forever. So when they do make contact with each other and they sort of like spread out, they're going to eventually make a line. Okay, now here's a general picture that we can draw for this one. I do have to start with 2 planes, so what I'm going to do is start with, I guess, like a profile picture. Okay, there would be a plane that has some depth into the paper here. Same thing right there, so I'm looking at one vertical plane, looking at one horizontal plane. Okay, now to give it some depth, what I'm going to do is just extend these little segments off of all of the endpoints. Okay, and I'd want to draw all those to be the same size, and then we're going to connect them. Hopefully they're the same size. There's going to be a little break right there where the other line goes through. Oh, and then you've got one more diagonal that you draw, which is right there. Okay, so that'd be a picture of 2 planes that are intersecting. If those planes intersect, then their intersection is going to be exactly one line. All right, so that line is here. That's where that would be. And last, postulate 7, if 2 points lie in a plane, then the line containing them lies in the plane. All right, so for that, I'm going to need to start with 2 points and also a plane. Okay, so let's go ahead and draw the plane. Okay, so I got my plane. Now what I'm going to do is place a couple of points in there. So that's all the beginning part. If 2 points lie in a plane, then the line containing them, containing those 2 points, will also lie in the plane. Okay, so what that means is, well, imagine this first. We have a flat surface, maybe like a tabletop. Of course, the plane goes on infinitely in all directions, but just go ahead and imagine it as a tabletop here. If you put 2 points on top of it, and then you go and draw a line to connect them, that line is going to be drawn on top of that table. That line is going to be in the plane. It'll exist within that plane as well. In addition to the 7 points, lines, planes, postulates, I want to talk about the algebraic properties of equality. The algebraic properties of equality are essentially things that we do when we're solving equations. Okay, we usually describe these things as adding a certain amount to both sides, subtracting a certain amount to both sides, etc., etc. And then we have some things that are called substitution, also distributive property. These, like the postulates, are all things that we don't need to prove. We accept them as truth. Okay, like the addition property of equality, just add that abbreviated, but that's equality here. The addition property of equality says that if you had an equation written as A equals B, so it's like 5 equals 5, okay, but you got two things that are already equal to each other. These could also be expressions themselves. They could be more than just a number or a letter. But if you have two things that are already stated to be equal to each other, and you add some value, a C, or some expression, we're calling it C here, you add something to that left side, you add it onto the A. As long as you add that same amount onto the right side, onto B, then the equation is still equal. Okay, the subtraction property of equality, you have two things that are already stated to be equal to each other. If you subtract the same amount from both sides of the equation, your equation is still going to be true. It's still going to be equal. The left will still equal the right. You can do the same thing with multiplication. You can do the same thing with division. Okay, and then we got a couple other ones that are just slightly different here. The substitution property of equality. We start with an equation that we know to be true. Okay, we know that A is equal to B. Given with that. All right, then A can be used for B in any other equation. Okay, so if we are aware that A is equal to B, that these are the same thing, then in another equation where we're using the letter B, you can just swap it out with A. You can replace A, you can substitute the A in for B, or vice versa. If you have an equation that is involving A, you can substitute the B value in there. Distribution property of equality. This is your distribution property, okay? But what it's really saying here is that if you have a value that is outside of some parentheses, and in those parentheses, you're either adding or subtracting. Okay, I want to make that note here because it doesn't say subtraction in here, but if C is treated as a negative number, you can actually look at this as B minus C. So it's either adding or subtracting. If you have a value outside that is being multiplied by that set of parentheses with addition or subtraction inside of it, you can actually multiply the A to each of the terms that are in there. So we call that distributing in. You can distribute the A to the B with multiplication, and you can distribute the A to the C with multiplication. All right, as a little bit of a side note here, you can even go backwards. You can go backwards with this. Okay, if you notice that two things that are being added or subtracted have a common factor in them, you can divide that factor out, create some parentheses, and put that factor on the outside. Now, technically, that is referred to as factoring. That's what we call factoring, but it comes from the distributive property, so you can also refer to it as the distributive property of equality. All right, for this video, I really only have one example to go through. What we're going to do in that example is solve an equation. Okay, these solving techniques should be things that you are already familiar with, that you should be capable of doing. But what we're going to do with this is we're going to identify every one of the steps that we use as one of the algebraic properties of equality. What I'm going to do is work out this equation over to the left. Okay, and as I go through it, I'm going to write down all the steps that I do. So if I add something to both sides, I'm actually going to indicate that I'm doing that. Once I'm finished with all that math, to the right of it, I'm going to write down all the properties as they are referred to. All right, so let's start with our actual equation here. -4 is outside the 11x plus 2. And that's set equal to 80. All right, our first step. You could do one of two different things. You could distribute the -4 in. That's an option. You can totally do that. Or you can even divide the -4 out from the very beginning, because this is just a factor to the rest of the equation. Okay, so I'm going to go ahead and do that. I'm going to divide both sides by -4. These will cancel. That'll give us 11x plus 2. Over here, when that divides, that'll give us a -20. All right, on the left, we still got the 11, and we've got the 2. The 11 is being multiplied by the x. We're going to do that at the end because we've got to work our operations backwards, get rid of the weaker ones first. Okay, so that plus 2, we'll get rid of that one by subtracting 2 from both sides. And we end up with 11x over here is equal to -22. Okay, and then as our last step, We're going to divide each of these sides by 11. We're going to divide out that coefficient. And x will be equal to -2. That is your solution. All right, now to the right of this, what I'm going to do is write down all the things that I chose to do. I chose not to do distributive property. Actually, just sort of ignored that one and went with something different, which was division. Okay, so over here I used the division property of equality. I used the division property of equality. After that, I used the subtraction property of equality. And at the end, I used one more time the division property of equality. All right, so I divided, then I subtracted, then divided, and that got me through the whole problem. One of the reasons that we're doing it like this, that we're working out all the steps and we're writing down all the properties that we go along with it, is because in our very next set of notes, our very next video, what we're gonna do is look at what would be called two-column proofs. And in two-column proofs, whether they be algebraic or geometric, most of our focus is going to be on geometric proofs. You're going to have a left column where you actually do things, okay? And this will be called the statements. And then to the right over here, you're going to have an explanation of what you did over there, and we're going to call these the reasons. These will be called statements. These will be called reasons.
Wait, what?